Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. What we are discussing was the miscible displacement, that is what we are trying to build on in this lecture. More importantly, we have been talking about this process called dispersion, which is diffusion, that is mixing inside porous medium when a flow takes place. So, mixing because of flow inside a porous medium, that is what we are referring as dispersion, and how dispersion takes place in a porous medium, that is something which we have been working with. So, what we did so far was we had looked into the dispersion when dispersion as the flow takes place through a capillary. So, in this regard we have talked about so called tailored dispersion. We showed that if the velocity profile is uniform, that means when the front is uniform, when it is almost a plug flow inside the capillary, at that time the diffusion will follow certain equation. On the other hand, when there is a velocity profile, particularly a laminar flow in a capillary, which is the velocity profile, velocity distribution would be parabolic. In that case, pulse that you introduce, that pulse will be stretched in the form of a parabolic strip, and because of that the diffusion process, the mixing process is completely different. So, there are, I mean, what kind of theories they can that can be what kind of theories would be relevant here, we discuss those. Particularly the aim was that the diffusion in a static fluid, I mean, if I put a drop of ink in a beaker full of water, the way the diffusion takes place, we try to retain that same form. I mean, that is what Taylor has done. Taylor's dispersion is all about, Taylor's dispersion equation is all about that they have Taylor has retained that similar form of the equation, and then compared, okay, what would be the effect. I mean, when it is a static system, I can see, I can feel, okay, if I change this parameter, this would be the effect. Now, if the same equation form is retained, so one can extrapolate very quickly and see what would be the impact of various operating parameters when the flow is, when there is a non-uniform velocity distribution and still mixing is happening. So, all these things we discussed when there is a flow through a tube. Next, what we are going to do is we have talked about this dispersion when the injected when the solute is injected in the form of a pulse. That means, what we talked about at that time is that if you have a conduit here and if we introduce a pulse, that means we approximated it as a Dirac function, and its value at time t equal to 0, its value is infinity at z equal to 0, and away everywhere it is 0. So, this is a Dirac function. I mean, this is a Dirac function, and then this Dirac function, as it travels through these capillary, what would be the, how the flow would, how this concentration profile, how it would be flattened. So, it would be flattened like this, because it is continuously there is diffusion going on with the upstream and the downstream fluid. So, that is this broadening we have talked about, and we have already put together equations for it under two situations. Under one situation the profile is uniform, and in the other situation one has a parabolic velocity profile, which we call tailored dispersion. So, what are the form of equations, what are the impacts if radius changes, that means radius of the capillary changes, will it be more broadened or will it be more sharp. So, those discussions we had. Now, instead of instead of a Dirac function, instead of that, if we impose a step change here, if we impose a step change in concentration, how we impose a step change in concentration? The concentration was 0 all along or some value all along, and then suddenly we had, suppose there is a flow taking place and there is a toggle, we have there is a valve which we could turn, so that the flow is taking place from a different chamber which is than the one we had earlier. So, here there is a change in concentration, that means I have two chambers, one was pure water, let us say, and the other was water with salt or water with dye, and then from one chamber there is a switch. Now, at some time suddenly this concentration changed from 0 to some value, and then it continued to flow with that value. So, we continue to flow from that chamber. So, one can implement a step change here at the inlet. So, how it would come out at the outlet? So, at the outlet we said, in fact we briefly touched upon this issue, that one must ensure that, see, if we talk about the concentration at the outlet, definitely it will be 0 for some time, because these step change, it has to travel all the way through these capillary. So, there is a residence time. Any fluid that enters into this capillary, there is a residence time, after which I expect this to arrive at the outlet. So, that residence time depends on what is the volume of this capillary and at what flow rate we are injecting this, assuming the entire cross section is participating in the flow. Of course, I mean, suppose there is a dead zone inside for some reason, that there is a stagnant zone inside for some reason, that is not there. I mean, if we make some assumption that way. So, we can assume that after you inject this total volume of the, whatever is the volume of this capillary, after you inject that much of volume, you expect this step change to arrive at the outlet. So, it is if we plot concentration versus, I can say, I mentioned this before, that either you can plot it as time or you can plot this as cumulative flow. So, we mentioned this in the context of pulse. Now, in case of a step change also, after this residence time, if there is no stagnant zone, entire volume is available for flow, then one can expect that this step change will arrive now. So, the step change should have arrived here, but fact of the matter is that this step change will not be as sharp as it is, because you remember we had a Dirac function and we found that got broadened. The same thing will happen here also. This step will also, there would be diffusion with the downstream fluid, there would be some diffusion. So, because of this diffusion, this step change will also be somewhat smeared. So, this concentration profile would be something like this. Instead of a sharp step, it will be smeared. So, this is something which we are expecting, and so this instead of a sharp change, we have this smeared front, we can call it smeared front, and this smeared front is happening because one has this diffusion is going on. So, this is also a part of dispersion process, right. Only thing is there, so the only difference in boundary condition, if you look at there, these at t equal to 0, you have imposed an Dirac function, and instead of that here you are imposing a step change. So, now if we try to articulate what we are talking about here, diffusion of a concentration front. So, we are talking about a step in static system first. Okay. So, this analysis we are talking about here is basically for static system, not for the flow system, but our aim is to go to this flow system. So, first we apply this to the static system. So, what does static system, how do you define it? It is that you have z which starts from z equal to 0 here to z equal to infinity all the way, and the concentration at z equal to 0 is all along held at this concentration C1 0. Okay. So, initially these entire concentration from z equal to 0 to z equal to infinity, This concentration was, let us say, this concentration was, let us say, how do we define here? C1 infinity. So, let us say this concentration was C1 infinity. So, I would say then this z axis is this is probably the z axis, and this value is C1 infinity and this value is C1 0. So, for at time t equal to 0 for all z, C1 was equal to C1 infinity, this is the value. And then for t greater than 0 at z equal to 0, C1 is equal to C1 0. So, this is what you imposed from for t greater than 0. So, t is equal to 0, this entire domain of z equal to 0 to z equal to infinity, entire domain is at concentration C1 infinity. Then for t greater than 0, so moment the counting starts, this concentration at z equal to 0 is held at C1 0 and that is retained that way for all values of t greater than 0. So, because of this, one can expect that there would be diffusion from this side to that side. So, that means one can draw a differential element, one can find out how much would be the flux from left side, how much would be the flux from the right side, area perpendicular to the screen is A. So, how much would be the volume of this differential element if we multiply this by the corresponding delta C, if there is a change in concentration delta C. So, we can draw a mass balance, how much of mass, so many kg is entering over duration delta t, how much of kg is leaving from the right face of this differential element and how much is accumulation. So, we can do that same exercise, I had done it in previous lecture, and one can arrive at so called Fick's second law, which says that del C1 del T, the concentration here in this domain changing with time. So, C1 is a function of Z and T, del C1 del T is equal to d del square C1, C1 is a function of Z and T, del square C1 del Z square. So, this is the governing equation for a static system, no flow, nothing. This block was at a concentration C1 infinity. Suddenly, moment the time counting starts, concentration at z equal to 0 is held at C1 0, and from that point on we are trying to track the concentration in these domains z equal to 0 to z equal to infinity. So, obviously, if we solve this equation, I mean intuitively we can see that the concentration will gradually rise. You remember when we had a Dirac function, we found that concentration started rising here, right, because there was diffusion taking place. So, here also by the same token there would be diffusion from left to right, and because of that the concentration will rise. So, these are the lines, and these are the lines as time increases. I have given this by this arrow t with arrow showing upward, that means as t increases these would be the lines. What is the end of it? At t equal to infinity, if you continue, you expect this entire domain to be equal to C1 0, right. So, that is the end point. So, this is slowly this concentration will increase, and so in that case if we try to put these boundary conditions here or initial and boundary conditions, the initial condition is at t is equal to 0 for all z, C1 is equal to C1 infinity. So, at time t equal to 0 everywhere it was C1 infinity. Then as time starts t greater than 0, z equal to 0, that means at this end C1 is equal to C1 0, that is what you are imposing. And then at t greater than 0, that means when the time started, z equal to infinity, that means far away from this whole things, that far away from this location where things are happening, far away this effect of this will not be felt, because our domain is from z equal to 0 and z equal to infinity, not a finite domain. So, at z equal to infinity, C1 will remain unchanged. So, z equal to infinity, C1 will remain to its original value C1 infinity. So, with these boundary conditions and with these governing equation, one can solve and find out what is the concentration, what would be this concentration profile. Just like we had a concentration profile, I have given you that profile based on similar governing equation, but different set of boundary conditions. So, now if you try to solve this equation, we have generally the solution can be given as this. This is the solution. This is the solution. C1 0 is the concentration at z equal to 0 which you have imposed. C1 infinity is the concentration that was existing at time t equal to 0 everywhere in the entire domain. Z is the z distance and divided by 4 dt. So, basically this concentration is a function of position, time and diffusion coefficient or diffusivity, and this is called error function. Okay. This kind of solution is it is a very standard solution, and if somebody wants to get to this solution, one can think of the very basic steps would be here. One can first of all take when you work with this governing equation, first of all one needs to take the Laplace transform, and the Laplace transform if you take it can be solved by similarity variable also, but if somebody chooses to do this by Laplace transform, then it would be P C 1 bar that is equal to d square C 1 dz square. So, this is if you take a Laplace transform of this, you will end up with this form, and then if you take these, if you solve this, or you can write this as d square C 1 bar dz square minus p by d C 1 bar that is equal to 0. This could be a way out, and then you can solve this equation. You can write in that case it would be probably better to write this as in fact, since we are not this is true if we assume C 1 infinity to be 0, then probably this is the way it is. Otherwise, it is better to define a deviation variable. I mean it is if you are working with C 1 infinity to be 0, that is fine. Otherwise, I think I should be talking about some other variable C 1 prime here. This entire thing has to be expressed in terms of a deviation variable, so where C 1 prime is equal to C 1 minus C 1 infinity. So, one has to define a deviation variable, and then it is this is the transform variable is I am putting it in as a bar. So, this is C 1 prime bar. So, this would be the equation here, and if you solve this, one can get C 1 prime bar is equal to, it would be the solution would be a 1 e to the power m x plus a 2 e to the power minus m x. So, that means let us say I put a constant b 1 e to the power square root of p by d z plus b 2 e to the power minus square root of p by d into z. So, in that case one can have, if this is the solution, then one thing is noted at this point, that at z is equal to infinity, C 1 is finite, but here in this case if you put this as infinity, this will not be finite. So, the only way you can make this finite is by holding this b 1 as 0. Okay. So, when you use this boundary condition, so automatically b 1 would be equal to 0, and b 2 would be simply equal to C 1 0 prime bar. Prime means making it a deviation variable. Instead of calling it C 1 0, you are writing C 1 0 minus C 1 infinity, and bar means you are taking the this is the transformed variable. So, once you write this, and on top of that one can write this C 1 0 prime bar, one can, if you look at the true definition of Laplace transform, that is equal to 0 to infinity C10 minus C1 infinity into e to the power minus py dy. That is the definition of Laplace transform. And if you now take C10 and C1 infinity, these are constant. So, if you take this out, C10 minus C1 infinity, and then if you do this integration of e to the power minus py dy from 0 to infinity, these would be simply 1 by p. So, in that case you can write C1 prime bar, that is equal to 1 by p C10 minus C1 infinity e to the power minus square root of p by d z. So, that becomes the concentration profile if you follow the Laplace transform. And then if you go to the table for Laplace transform and go to the and take the inverse Laplace transform, so then automatically the equation that I mentioned will simply follow. That means, in that case you will be ending up with so called C1 prime would be equal to C10 minus C1 infinity into 1 minus error function of actually this should be p, this should be p. Okay, that doesn't matter because it's a limit to the integral. It can be p t dt. So, it is error this should be t and this should be here t. 1 minus error function of z divided by 2 square root of dt. So, so this is after you take inverse Laplace transform, you get this quantity, and the C1 prime is once again is equal to C1 prime is a deviation variable. So, it is C1 minus C1 infinity. So, this could be the chain of thoughts one can get to. Okay. So, this is a very standard equation with this kind of this type of boundary condition, and this solution in terms of error function is very common. And one needs to know this that this error function, if you look at this the error function, the way error function plot is, if somebody plots say error function of x as a function of x, it is generally it remains linear from 0 0 it goes all the way linear, okay, up to 0.65 0.7 around that, and then it starts carving out, and the idea is that error function of 1, the limit would be 1.0, asymptotically it reaches 1.0 as x tends to infinity. Similarly, on the negative side, error function of minus x would be minus of error function of x, and here also it will follow the similar trend and asymptotically reaching minus 1 as x tends to minus infinity. So, this is a error function typical behavior of error function. Okay. So, now this is, now that we know this, let us look at the solution once again. So, this was the solution we have C1 minus C10 by C1 infinity minus C10 equal to error function of z divided by square root of 4 dt. So, this gives me in static system what would be the concentration profile. That means, I have given a step change. So, I see that the concentration gradually rising as time progresses. So, as time progresses, as time increases, concentration is gradually rising, and it will this concentration at any point, at any z, at any time, it would be following this equation. So, when C1 infinity is equal to 0. That means truly, I mean, earlier we had held this as C1 0 and these as C1 infinity, right. So, when this is truly this is C1 infinity is 0. So, that means it is going all the way to 0. Then we can simplify this further, then C1 ZT becomes equal to C0 into 1 minus error function of this quantity. Now, one thing you must note here, now suppose gradually what we would do is, we have this is what is happening in the static system. So, what next we will do is, we will take this up to the flow system. Flow system, obviously, if we are working with a plug flow, we can say that we have to go for a moving coordinate system, as we had done earlier. That time we had z square. So, instead of z square, I am talking about for the pulse, for the Dirac function, there or in Taylor dispersion everywhere, we had this z e to the power z square term, right. So, in that z square, we have to write it as z minus u bar t whole square, right. When we had a uniform velocity, it is and when we have these, it was v naught, the average velocity in case of a Taylor dispersion. So, we had to go for a moving coordinate system. That means, we assume that this whole thing that we have here it is a static system. Now, as if this tape is moving in z. So, that is why we had to go for a moving coordinate system. That is one thing that we must note. And second thing is, when you give a step change in concentration and then you expect this to travel, or step change with time would be then, this is with space. So, step change with time would be this. So, as this concentration step change travels, we said that we have only looked into this part of the concentration, assuming C10 to be fixed. But when you implement a step change, C10 will not be fixed. C10 will also, because I am not maintaining C10 here. Something is diffusing out from here. Moment something is diffusing out from here means here also some loss would be there parallelly. This side you have a gain and you are assuming there is no loss from this side, C10 is maintained. So, that will not happen when you put a step change, because something is traveling to the, something is diffusing into the downstream side means there is a loss in the upstream side. So, that also has to be accounted. So, this is something which we would be addressing in the next class, and we will continue. So, keep this in mind that we have to now all the understanding of static process that we have to extend it to a flow system. And in the flow system, obviously there will be a moving coordinate, number one. Number two, as we have assumed in static system, C10 is, I maintained it as fixed, but that is not possible in a flow system, because any gain on the downstream side there has to be an equivalent loss in the upstream side, that also has to be accounted. So, these are the things we will discuss in the next lecture module. So, this is all I have as far as this particular module is concerned. Thank you very much.